Good afternoon, everyone. I am Hemant Verma, and today I will talk about silicon nitride microcantilever-based temperature sensors. So there are various commercial sensors, temperature sensors in the market like RTDs, thermistors, thermocouples, and there are various pros and cons in terms of response time, temperature resolutions, and like the range of operations. The regenerative temperature sensors have potential applications to overcome all the demerits that's present in the commercial sensors, like the minimum resolutions that we can go. So, and that this is not working. It's not working. Okay. So, this is the outline of my talk where I will discuss about how a regenerative sensors work, then discuss about the device fabrication and the circuitry involved to measure the response of the devices, and then I will talk about my temperature sensing result and finally conclude my presentation. So, see, any resonator, either it's a cantilever or a beam or a membrane, it will have some resonance frequency, and that frequency will be proportional to this K effective and that stiffness in this mass term. So, if some external stimuli acting on this resonator, it's either stiffness changes or mass changes, and due to this the frequency will either shift, it's either increase or decrease. So, due to the stiffness change the frequency will increase, and due to the mass change the frequency will decrease. So, just by measuring this frequency shift, amount of frequency shift, we could be able to measure the amount of the external stimuli acting on these sensors. This kind of sensor can be used in various applications like mass detection, like as of now people are measuring mass in ectogram range with this regenerative sensors. People are using it for, there is some issue with this. It can be used for disease detection, it can be used for humidity sensing. So, let us discuss about the device fabrication thing. So, for fabricating our devices, I have used highly doped silicon wafer, and that is the substrate. On top of this substrate, I have deposited this silicate glass which acts as a sacrificial layer, and then I have deposited silicon nitride, and that is the structural layer for my device. And it is basically a three-step lithography process. So, in the first lithography process, I have defined this cantilever. Then after this, I have deposited this metal piezoresistor. So, in order to detect the response of this cantilever, and in the third litho process, I have deposited the metal pads to take the connection to the outside circuitry. And finally, the cantilever is suspended with wet etching and critical point dryer process. There is some lag in this. Okay. Anyway. So, these are my SEM image of the fabricated devices. Now, in order to measure the response of this device, I have used capacitive actuation and piezoresistive detection. So, here you can see there is one piezoresistor on top of the cantilever and rest 3 is on fixed base. So, initially when the cantilever is at rest position, the resistances are in all 4 arms are equal, and when I bias the opposite 2 nodes and from the other 2 opposite nodes, I am taking this voltage output signal, it is passing through this differential amplifier and going as input to this lock-in amplifier. So, when the device is not actuating, all the resistors are equal and there is no voltage output at these 2 nodes. But once we start actuating our devices with this voltage, this AC voltage, so basically due to this capacitive forces, the devices will start actuating with some frequency that is defined by this AC voltage that is applied through this lock-in amplifier, and this also acting as a reference voltage. So, with this the resistance in this one arm changes, and this causes the unbalance in this of this Wheatstone bridge, and this causes a voltage output in this 2 node. And since at resonance frequency there is the maximum amplitude of this resonator, this causes a large change in resistance of this arm and we get a maximum voltage output. So, based on this, this is the data for the amplitude versus frequency response for different actuation voltage. You can see with the increase in voltage, the device response increases, its amplitude increasing. And after certain actuation voltage, you can see there is the sudden jump in amplitude. So, basically this device is showing non-linearity after a certain voltage. The second graph depicts the same thing, but here you can see initially till 60 volt the device response is linear, but after 60 the device reaches to the non-linear region and the amplitude starts saturating. So, this data we basically use to calculate the frequency stability of the device. I will discuss about the frequency stability in the next slide. So, sorry. Yeah, so frequency stability will be proportional to this quality, depend upon this quality factor and this signal to noise ratio, which we can again define in terms of this dynamic range of the device and quality factor. So, dynamic range is basically the logarithmic ratio of the maximum signal that we can measure in the linear regime. So, basically the maximum critical amplitude and the minimum signal that we can measure through this device. So, the minimum signal for a resonator will be the thermomechanical noise of the device. And if we could not measure the could not able to measure the thermomechanical noise of the device, then it will be the noise floor of the device, and that will be combine some of the noise floor from the device and the measurement circuitry that we are using. So, see, let us discuss what frequency stability is. So, if we have any resonator, it will have some resonance frequency, and when we apply a force, a harmonic force, it will resonate at this resonance frequency. But in real cases, there is always some fluctuation, and that causes the resonance frequencies to fluctuate around its mean value. So, frequency stability basically defines how will the resonator response give the same frequency offset over a period of time. And with this data, we basically calculate the temperature resolution, which is proportional to will depend upon this frequency resolution term and this temperature responsivity term. This frequency resolution basically we calculate from this frequency stability data, and this temperature responsivity I will discuss in the later slide. So, we measure this frequency stability experimentally with Allan deviation. So, in Allan deviation, it's what we do, we basically measure the phase response of the resonator at its resonance frequency over a period of time, and then we convert this phase response into the frequency response, and we put this value in this equation. This is just like the standard deviation, but in Allan deviation we basically take adjacent difference instead of subtracting this value with this mean value. So, this Allan deviation is a function of integration time, and you can see in this curve, the blue line shows the experimental data when we actuate our devices at the critical amplitude, where the devices is in nonlinear in linear regime. So, the maximum stability is at 1 second, and which is about 4.29 into 10 power minus 7, and based on this the frequency resolution is about 0.18 hertz. But theoretically, if we consider the thermomechanical noise of the device, we could able to measure the we could get the frequency resolution of about 4.2 millihertz and the frequency stability of about 1e minus 8. But at this time, we due to some circuit restriction, we could not able to measure the thermomechanical response. So, after this, since we got this frequency resolution and frequency stability data, the next is the frequency response of the device. It's not working. Yeah. Okay. So, for the temperature sensing, we have performed the temperature sensing in the cryo state, and see, you can see once we are decreasing the temperature, the device frequency start increasing, and the temperature responsivity, which is basically the slope of this curve, is about minus 5.8 hertz per Kelvin. And if we divide this value with the resonance frequency value of the device, we will get about minus 14 ppm per Kelvin response of this device. So, since we know that the resonance frequency of the device, as I have explained in the first slide, that it depends upon the stiffness and mass term. So, the stiffness is proportional to this Young's modulus and this geometrical parameter. Again, this mass will depend upon the density and this geometrical parameter. So, based on this, we calculate the temperature coefficient of frequency, which will depend upon these two terms, this stiffness, change in stiffness term and this change in mass term. So, if we write it in terms of this Young's modulus and this geometrical term and density term, so the final value will be it will depend upon this temperature coefficient of Young's modulus and temperature coefficient of linear expansion. So, since I've used silicon nitride as structural material, so for this the temperature coefficient of Young's modulus is about 3 ppm per Kelvin, and the temperature coefficient of temperature coefficient of linear expansion is about 3 ppm per Kelvin, and for temperature coefficient of Young's modulus is about 48 ppm per Kelvin. So, based on this the theoretical temperature coefficient of frequency is about minus 25 ppm per Kelvin. But experimentally we are getting about minus 14 ppm per Kelvin. This slight difference may be due to the fact of the thermal stress present in the cantilever, which basically reducing the stiffness of the cantilever. So, this value I have used to calculate the temperature resolution. Frequency resolution we have already calculated in the previous slide, which was about 0.18 hertz experimental frequency resolution, and this is the temperature responsivity, which is about minus 5.80 hertz per Kelvin. So, based on this, this is the minimum frequency resolution that we can measure with this device, and this is about 2 order higher than the commercial sensors available in our market, like the RTDs, thermocouples and thermistors. And if we compare it with the previous resonator based sensors, so for the NEMS devices like the membrane or a nano beam, although the temperature coefficient of frequency is higher than this work, but we are getting about an order of improvement in temperature sensitivity. That is due to the better stability of our devices as compared to theirs. So, in conclusion, conclusion slide. Yeah, in conclusion, previous one. So, we have made this self-sensing micro-cantilever, and we have got an order of improvement in temperature resolution as compared to the previous NEMS devices, NEMS resonator based sensor, and about 2 orders improvement in resolution for that commercially available sensors. And these devices have linear response over a wide range of temperature, and also like this can find application in bolometer and temperature probing, where we require a precise temperature resolutions. With this, I will conclude my slides. So, this is my group at SENS ISC Bangalore, and I would like to thank MNCF and NNFC at SENS, where I have fabricated and characterized my devices, and I would like to thank Semiconductor Laboratory Chandigarh, where I was getting the devices. So, I am open for the question now.